Lucky has come with his father to see their new house. The house is almost finished, only the lighting work is left. Just then, the contractor also arrived there.
Here are some bulbs. You can choose whichever one you like and I'll have it installed. All 5 of these bulbs range from 10 to 30 watts, but this one is the best. We supply this one ourselves, it's just a bit expensive. Hey, which one do you think is best, Lucky? Higher wattage means a higher electricity bill, but you'll also get more light. Let's do this. Let's go with something in the middle. Yeah, then just go with mine. It's 20 watts.
When Lucky looked at the bulb, there was no power rating written on it.
All the others have a power rating, so why doesn't this one? Oh, they didn't print it to save on printing costs. Trust me, it's definitely 20 watts.
But Lucky wasn't convinced. Is there any way to find out the power rating of this bulb? Just then, he noticed the ratings on the other bulbs, and 2 of them formed a common ratio in combination. He remembered Rajwan sir's physics class.
Today we will study Wheatstone bridge. This is a technique where we can determine the value of an unknown resistor with the help of known resistors. In a Wheatstone bridge, 4 resistors are connected in parallel like this, and in the middle of the bridge, another resistor, such as a bulb, is placed. This bulb will only go out when the Wheatstone bridge is balanced. That is, the ratio of these resistors will be equal to each other. But sir, how will that happen? Because when the bulb goes out, it means the voltage at these 2 points is equal. If we assume the current in the left branch is I and in the right branch is I dash, then the voltage drop across R1 will be I times R1, and across R3 it will be I dash times R3. For the voltages at both points of the bridge to be equal, the voltage drops across both resistors must also be equal.
That means I times R1 will be equal to I dash times R3. From here, the ratio of I dash to I comes out to be R1 divided by R3. If we apply the same logic to R2 and R4, then the ratio of I dash to I from there will also be equal to R2 divided by R4. That is, R1 divided by R3 will be equal to R2 divided by R4.
This means that if the bulb is not glowing and we know the values of any 3 out of these 4 resistors, we can easily find the value of the 4th one.
Lucky applied this very concept to bulbs and arranged 4 bulbs whose power ratios were equal in such a way. And to check whether there was current in the middle bridge, he placed a 5th bulb there.
But the Wheatstone bridge works for resistors. Will it work for power as well or not?
It will work because power is V squared divided by R. From here, the value of R becomes V squared divided by P. The power of a bulb is specified according to the voltage supplied in our homes, and if you pay attention, R is inversely proportional to P. That means if the power of one bulb is twice that of another bulb, its resistance will be half. So, in a balanced bridge, the ratio of the resistors is exactly the inverse of the ratio of the powers. And if you notice, this ratio remains the same for all 4 bulbs.
So if this bulb is 20 watts, then this will form a balanced Wheatstone bridge, and no current will flow through the middle wire.
Lucky turned on the circuit switch. But what's this? The middle bulb lit up, which means it's not a 20-watt bulb,